somewhere. It gets released as it moves down the electron transport chain, and as that gets emitted, some of it gets captured for the cell to use as ATP. And we're going to go through the whole process today. Not today, we won't have time to go through it all today. We're going to introduce it today. But we're going to have to understand redox reactions. Because if something gets oxidized, something else by definition has to get reduced. So I want you to think about electrons, and I want you to think about electrons moving. And I also want you to imagine in your mind going from a high energy state to a low energy state always gives off energy, and is always preferred by the electron. So the electron always wants to move to a lower energy state. And the analogy that I can always think of is if you're on a tightrope over the Grand Canyon, you are at a high energy, unstable state. You are not relaxed, you are not happy, unless you're crazy. Most people are not going to be happy. They're nervous, they're lots of energy, a lot of potential energy because you're high up above the Grand Canyon. And imagine taking that energy and then all of a sudden you're on your couch watching like Jimmy Fallon or Jimmy Kimmel or whatever show you like to watch. You're relaxed, you're happy, you're where you want to be, you're in a much lower energy state. And so imagine that there's a great energy loss when you go from your tight wire above the Grand Canyon to your couch in your home with your snacks watching your show. And that you want to be in this more calm, relaxed state, and that there's a lot of energy that's given off in the process. And we're going to be trying to capture that energy that's given off in the process. Okay. So breaking down all of those organic molecules is exergonic, which means they're going to be giving off energy. So things that are catabolic, breaking down, give off energy, which means they will happen spontaneously, which means they're exergonic, which means they have what kind of delta G, positive or negative? They give off energy, it's okay. Negative. So keep all of these terms. Catabolic, spontaneous, exergonic, negative delta G. Anabolic, positive delta G. Non-spontaneous, endergonic. So keep those two kind of pools of words separated from each other. We'll talk about fermentation later, but just to introduce it to you quickly, this is degradation of sugars that occurs without oxygen. And it's actually still a very important process. Fermentation is how we make cheese and beer and wine and kimchi, if you like kimchi. So a lot of things are made through the process of fermentation. We break down a lot of sugar molecules this way, but it's not how our cells break down material. So we'll talk about fermentation later on, but just know now that this is where we're going to be degrading sugars in the absence of oxygen. And what our cells prefer to do, our cells can break down in the absence of oxygen, but it's not very efficient. The best way for the cell to get the biggest bang for its buck is to undergo aerobic respiration. And that's what we mean. We can use those two terms synonymously. When we talk about cellular respiration, we're really focused on aerobic respiration. Aerobic just means it's in the presence of oxygen. So we're using oxygen along with organic molecules, sugar, protein, fat, you name it. We're going to pick glucose just as an easy start. And in the process, we're going to be yielding energy in the form of ATP. We'll also give off carbon dioxide and water. And again, it just points out that technically cellular respiration includes both aerobic and anaerobic, but we just are going to be using that term to refer to aerobic respiration. It's oftentimes reserved for that. And also, as I've already mentioned, all of these organic macromolecules that we spent all this time building, with the exception of nucleic acids don't store energy, but all of these can be burned as fuel, basically. So we can use all of them as a fuel source, but we're going to just pick glucose as the molecule that we're going to trace through this process of cellular respiration. And as I've already mentioned, this is all going to happen because we're going to be transferring electrons from one atom to another. And we're going to be going from a higher energy state in a stepwise fashion to a lower energy state. And with each step along the way, we're going to be giving off a little energy that the cell is going to capture. So just keep that stair step, a little bit of energy, as the electrons get transferred from one molecule to another down the chain. And so we've already introduced this term now, oxidation and reduction. And again, by definition, if one thing is getting oxidized, another thing has to be getting reduced, because you can't, electrons don't just float around unattached. So if something is losing electron, then something else has to, by definition, be gaining an electron. And so oxidation is the process of losing electrons. And then reduction is the process of gaining electrons. So one of the reasons that these terms can get confusing for individuals is because something that's really good at stealing electrons, at oxidizing things, is called a reducing agent. And things that are really good at grabbing electrons, well, let me give you this other term before we go to that another. Give me 1 second and I'll come back to this idea of what's the difference between a reducing agent and an oxidizing agent. But here's one example of a redox reaction. So here we have sodium. It's losing an electron. So we're going from a neutral charge to a plus charge because we have one less negative charge. So it's losing an electron. Oxidation is lost. That means it's becoming oxidized. Okay? Chloride, on the other hand, when we're making salt, table salt here, becomes reduced, which means it's gaining an electron. So that's just a redox reaction, a very simple redox reaction. And then this is just the general formula where you have an electron moving from one random atom to the other. One is becoming oxidized and the other is becoming reduced. The electron donor is called the reducing agent, and the electron receptor is called, or not, to say receptor, I should say acceptor, not receptor, sorry. The electron acceptor is called the oxidizing agent. So oxygen is really good at pulling electrons from other molecules, so it's considered an oxidizing agent, but it is reducing other things. So keeping these terms straight can be a little tricky. It takes a little practice, but you guys can get there. And we're also pointing out here with sodium and chloride, you can see that there was a true transfer of electrons from one atom to the other, but sometimes it's just a change in the electron sharing. So if you're going from an atom that's less electronegative to one that's more electronegative, that can still be considered a redox reaction because now one atom is pulling the electrons more tightly and the other one has them further away. So even if it's not a full charge, even if it's just what would be considered like a polar, a change in the polarity where you're now attached to a more electronegative atom, that's still considered a redox reaction. And so we'll give this example when we are reacting methane and oxygen. So this is methane. Methane gas is a greenhouse gas. Just heard an NPR story about it this morning. And here's oxygen. And these are our reactants, and we are going to be producing carbon dioxide and water, as well as a little bit of energy in the process. But our oxygen becomes reduced. Reduction is gained because now the oxygen, right here you can see the oxygen is sharing its electrons evenly because the oxygen has the same electronegativity. But when we get this product, which is water, remember oxygen pulls more tightly on those electrons than the hydrogen does. So even though it's the same total number of electrons in the water molecule and in the oxygen molecule, now the electrons are closer to the oxygen molecule, so it's still considered that the oxygen has been reduced because the electrons are closer to it, even though there's not a complete total donation or reduction in the total number of electrons. Does that make sense? Okay. So with cellular respiration, which is our example that we're going to be walking through, glucose is going to be oxidized and oxygen is going to be reduced. So that means if glucose is being oxidized, that means it's losing electrons, and oxygen is going to be reduced, which means it's gaining electrons. And it makes sense that oxygen is gaining electrons because oxygen is what? More electronegative. It likes those electrons. It's very greedy. It loves electrons. So it tends to be reduced quite commonly. So it's an oxidizing agent. So here is our oxygen becoming reduced to water molecules. And again, this is that same idea where it's not that it's gaining total number of electrons, but it's pulling on those electrons much more tightly, so the electrons are much closer to the oxygen molecule than they are to the hydrogen, they're closer to the oxygen atom than they are to the hydrogen atoms, so it's still considered reduced. And our
glucose molecule is going to become